Hello everyone, welcome back to my YouTube channel. Today, I've decided to start a new project modifying this 3-phase brushless motor, also known as a BLDC motor. I'm going to customize it so it can work perfectly with my jet propulsion system. As you can see, I have quite a few different versions of this motor here, but after taking a closer look, I've decided to go with the longer 2-to-1/7 version. The main reason is pretty simple for this project. I really need a motor that can deliver higher torque. A longer stator like this usually means better torque output, which is exactly what I'm aiming for, especially when adapting it for my jet propulsion system. What happens if you push a small BLDC motor to its absolute limit? Today, I'm taking the 2-to-1/7 and turning it into something way more powerful than it was ever designed for. But before I can push this motor any further, there's a major problem I need to deal with first: heat. When this motor runs at high performance, the temperature rises really fast, and that can seriously affect both efficiency and durability. So the next step is clear: I need to extend the motor shaft and design a custom cooling solution to improve heat dissipation. If I don't solve this, the whole setup won't last long under heavy load. Now, this is where things start to get risky. To extend the shaft, I'm going to use 2 brass couplers, weld them together, and turn them into a single solid piece. Sounds simple, but it's actually a critical step. Because if this part isn't perfectly aligned, even the slightest imbalance at high speed could cause serious vibration. Or worse, completely destroy the motor. On one end, I'll create a flat surface to mount it securely to the motor. And on the other end, I'll machine threads to install a bearing, which will connect to the jet blower housing. If everything goes right, this will give me a strong and stable setup. But if it goes wrong, this could fail spectacularly. And now, it's time to refine this coupler and make it as precise as possible. Because at high speeds, even the smallest imperfection can throw everything off balance. A tiny misalignment here could lead to vibration, loss of efficiency, or even total failure. So I need to machine this part carefully and make sure everything is perfectly aligned before moving on. To make sure everything stays perfectly aligned, I'm connecting these to brass couplers using an aluminum tube. This isn't just for structure, it's critical for keeping both ends perfectly concentric. Because at high RPM, even a tiny misalignment can cause serious vibration and instability. So this aluminum sleeve will act as a guide, helping me maintain precision and keep the entire shaft perfectly on axis. At this point, things are actually pretty straightforward. All that's left to do is align everything properly, connect the parts together, and secure them in place using screws. Simple in theory, but if anything is even slightly off here, it could cause problems later on, so I still need to make sure everything is tightened down perfectly before moving forward. This motor can spin at over 50,000 revolutions per minute, so everything has to be absolutely smooth and perfectly balanced. At those speeds, even the smallest imperfection can turn into a serious problem, causing vibration, instability, or even catastrophic failure. There's no room for error here. And next, we move on to the motor controller. This is basically the brain of the entire system and one of the most critical components, because whether this motor runs smoothly or not depends heavily on this. A good controller means stable performance. It uses a new generation of MOSFETs, allowing it to handle over 100 amps of current. That means significantly more power and much better performance under heavy load. This is what's going to push the motor to its limits. With this ESC, I can control everything using the M32 software. It gives me access to a wide range of parameters like startup current, soft start behavior, and many other critical motor settings. This level of control is extremely important because it allows me to fine-tune the motor for smoother operation and much more stable performance. Basically, it lets me push the system harder while still keeping everything under control. Because this jet blower pulls a huge amount of current, power stability becomes a serious issue. So to handle that, I'm adding 2 large capacitors to the system. Their job is to smooth out voltage fluctuations and absorb sudden current spikes. Without them, the voltage could drop or spike under load, and that could make the whole system unstable, or even damage the controller. So these capacitors are absolutely critical for keeping everything running reliably. Alright guys, so at this point, we've completed some major steps modifying the motor, redesigning the electronics, and getting everything ready. Now it's time to show you something I've been working on for a long time. This is my brand new design, a fully 3D printed jet blower housing. I spent days, actually a lot of time refining and modeling this to get it just right. And honestly, I'm really satisfied with how it turned out. On this design, I've added a lot of ancient Maya-inspired patterns across the body, including the main housing, the handle, and even the battery base. The goal was to give it a more aggressive, bold look, while blending modern engineering with a touch of ancient style. So it's not just functional, it also has a really unique aesthetic that stands out. For this blower, I didn't just focus on looks, I also put a lot of thought into the aerodynamics. The design channels compressed airflow from the top and directs it down across the underside of the electronics. This helps actively cool critical components like the capacitors, MOSFETs, and even the wiring. And that's extremely important, because this system runs at very high performance, pulling up to 50 amps of current. At that level, heat becomes a serious challenge, so the entire cooling system has to be carefully designed to keep everything stable and reliable. The entire system is assembled using screws, so everything is locked together into one solid structure. Now it's time for a real-world strength test. I'm going to check both the weight capacity and the overall rigidity of this housing. I weigh around 80 kilograms, and I'm about to stand directly on top of it. Let's see if it can handle the pressure or if this is where everything breaks. Wow! It only left a few minor scratches. I'm using PETG for this print, which has really high strength and durability. And as you can see, even with my full weight on it, there's absolutely no visible deformation. The structure held up perfectly, just a few surface scratches, nothing serious. That's actually way better than I expected. And now, it's time to bring everything together. I'm assembling all the components: the motor, the housing, the controller, the throttle trigger, and all the wiring. Piece by piece, everything comes together into one complete system. And just like that, we now have a fully built, high-power jet blower. For the wiring, I'm using high-temperature rated AUG cables. Since this system draws a massive amount of current, using high-quality wires isn't optional, it's absolutely necessary. Cheap or undersized wires could overheat, cause voltage drops, or even fail under load. So this is one of those details that really makes a big difference in reliability and safety. Next, I'm going to integrate a MOSFET-based switching circuit that works like a relay. This will be connected to a timer on the board, so after about 8 minutes of an activity, it automatically cuts off power to the entire system. The idea here is simple: when the system isn't in use, it completely shuts down to prevent unnecessary power drain and protect the electronics. This not only helps save battery, but also improves overall stability and reliability of the circuit. Alright, without taking up too much more of your time, let me show you the full internal setup of this handheld jet blower. Inside, I've added a dedicated heatsink for the switching MOSFET, because during operation, this component can get extremely hot. So I placed an aluminum heatsink right under the airflow channel. As air is pushed through the system, it flows directly over this heatsink, helping to cool it down efficiently. This setup should significantly improve thermal performance and make the whole system much more reliable over time. Next up is the impeller, and this is a critical part of the system. I had to dynamically balance it to make sure everything runs smoothly. At these kinds of speeds, every single component has to be perfectly balanced, because if it's even slightly off, it can cause vibration, damage the bearings, or even destroy the shaft. This blower spins at extremely high RPM, so dynamic balancing isn't optional, it's absolutely essential. The next step is pretty simple. I just need to connect the battery base to complete the system. And just like that, everything is done. This is my fully finished mini handheld jet blower, compact but incredibly powerful. And now, it's time for the real test. I'm going to measure the thrust using a scale, and then take it outside to see how it performs in the real world by blowing away leaves. Let's see how powerful this thing really is.
Khởi động thì bóp một cái, chờ 1 giây. Bóp một cái mà hết lửa cái máng của anh em ạ.